Yes, slides, excellent. Some AV issues there, so I guess I'll be skipping the demo, but yeah. I can show you afterwards, you can find me later. So yeah, it'll be a bit of a, probably a bit short on time now, so it's going to be a little bit quick, but thanks for having me back to talk about another Mojo bug. Hopefully this will be interesting. It's a bit of a change for me, talking about a bug that I didn't find. So we'll kind of start the story here. So this was a bug that was reported to Chrome late last year as being exploited in the wild. And it kind of immediately caught my attention because it's a really interesting bug. It's in code that I've looked at the code above it and the code below it and never quite looked at the code itself. And I was incredibly frustrated that I didn't find this bug and somebody else did, and they got to exploit it. You know, it was just like, it was a really bad time. So I'd been complaining about this for a long time, and some people in my team had said, like, you know, you should talk about this. So maybe they didn't mean, you know, in a presentation, but that's what ended up happening. So if you saw my talk last year, this might be familiar. It's kind of the layer cake that is Chrome's Mojo IPC. There are lots of layers. It's very complicated. We're going to ignore pretty much all of that today. We're only interested in the top 2 layers for this vulnerability. My slides are going to be a lot of code snippets. Please don't feel like you should immediately try to look at the code. I will be talking through the relevant parts, and the code is just kind of a structure to go through it. So we're going to talk through how the Mojo code looks, how the validation should happen, and what it means. Because the bug itself, without any context, is kind of not super meaningful to understand. So what is Mojo? It's an IPC mechanism. It's used to send messages both from untrusted, unprivileged contexts to privileged contexts, and also for privileged contexts to make function calls in unprivileged contexts. So both from renderer to browser, browser to renderer, renderer to GPU, every privilege boundary in Chrome will have some Mojo calls going across it. And what happens is in your client code, in this case C++, you'll have a handle to a remote, which basically is an object created in the generated code, which knows if you want to make a particular function call, how do I serialize all of the arguments and send them across that message pipe? At some high level, that basically looks like this, right? You have some block of binary data, and then maybe you have some handles associated with that. That could mean like file descriptors, right? Like platform handles. It could mean more abstract things like Mojo message handles, or it could be like shared memory region, or all sorts of stuff. Then on the receiving side, again, there's some code which knows what parameters it's expecting, deserializes that for you, and then passes that to the service. And then sometimes, if that function has return type, that's not just nothing, the service is going to pass data back to the receiver, which will serialize it, send it back to the remote, and the client will then get a call back. You know, that function you called earlier has responded because most of this is asynchronous, and like, here's what it sent you back. So I'm going to look mostly at one interface today because it's my favorite interface. This is the Blob Registry. This is a browser process hosted, so like privileged service, which renderers use to store like stuff. If you write JavaScript code, the blob object kind of, I guess fairly intuitively, maps in the back end to a call to the Blob Registry in the browser with some data, and it'll put it somewhere and look it up later. So we look at the first method call here, or method definition here, register. It has like a load of parameters stuff, right? That message that goes over the wire consists of basically this structure here, which is in the generated code, right? So you can see, starting below the validate function, right, we have some struct header, and then you can see like a field there for each parameter. Right? That's all we really care about here, right? There's some structures and stuff. So how is this actually used? Well, oh no, I'm doing structure first. Okay, how does that actually look? So obviously, we don't actually put pointers in IPC messages, right? We don't know or we shouldn't know the layout of the other process. So those fields, which are called pointers, right? They're actually going to be an offset, 64-bit offset within the message data. The structures, again, what we were looking at was a structure, right? So what do we have in that struct header? We have a number of bytes. We have a version. We have versioning here because actually, at least on Chrome OS, Mojo calls do happen between binaries built at different times. So you might actually have different versions of the same interface talking to each other. And if you have an array parameter, well, that's going to be a number of bytes, a number of elements. So you can see already in this, like the way in which these types are represented, it's pretty clear that we don't want to just trust this data across a privilege boundary, right? An arbitrary offset into a message body would be a bad thing to try and just like read. So if we look at where this code is used, so specifically the service-side dispatch code, there's no validation here, right? Like we just take the message payload buffer and we reinterpret cast it to that structure header we just looked at, and right, like if that was all the code there, this would be a really bad thing. So we'll go try to figure out where does that actually get validated. And in order to find that, we're going to go down from this generated code to this bindings layer. And if you follow the code through a bit, you'll eventually find the message dispatcher, which is the lowest level part of this receive dispatch pipeline. And that has this field validator. We call this method, is it indeed validated? If it's not validated, obviously we exit. And a validate function is going to look something like this, whatever. It validates all that stuff. We don't need to worry about it. But we don't just have parameters to methods. We also have these return types. So what happens in the second method of this interface, where we actually return some object from that function? We go back to the bindings code. We see a structure that's like basically the same as the one we saw before, right? But it has different fields. The point where that client is going to dispatch this response, we see again, we just have like a cast, right? So no validation here. So where does that validation happen? Again, bindings layer. So starting at the bottom where that message is dispatched, we can see, okay, like this kind of makes sense. We're responding to a function call we received earlier, right? So we have to be able to match up which function call is this a response to. So we get this request ID. We look which method calls are we waiting for responses to, okay? We found it, dispatch the call. The name of this function, handle validated message, I guess that does imply that validation already took place. So let's see if we can find that. And sure enough, if we look at where the actual message comes in, we have this call to dispatcher accept, and this is, again, like the message dispatcher path we just looked at. There's going to be some validation there. So how do we actually validate that message? This is the top level function for that validator. And if we look at the implementation, we can see, okay, yeah, this kind of makes sense, right? We have a message. We know what type that message is associated with. So we look up from the message header what function is being called, or what function is this returning from, and then we validate it according to the type. Seems to make sense. At this point, I guess the sharper people in the audience who have been very carefully watching the slides will be like, but here you're using this name field, and in the other code, we were using this request ID, and like, yeah, I mean, that's the bug here, right? So when we receive the return value from a function call, we're going to validate that data according to which function it says that it returned from. So, okay. But when we actually give that message to the callback, we say, which list of function calls do we have? Which function call ID, like, is this a response to? Not that there is no type there, right? So it's quite a it's quite a strange bug, right? And it gives us a very strange and sort of powerful primitive that we have this type confusion of an IPC message, but the IPC messages themselves are kind of C or like C structures, so it's not entirely a logic bug. It's kind of somewhere like almost a memory corruption issue, but not directly. What can we do with this, like, to progress further? In some sense, it has a lot of possibilities. In some sense, it's also very limited, because we can only type confuse messages between response types of functions in the same interface. So we need to find interesting interfaces with multiple functions with different return types, and we can then type confuse those return types. So we'll start off on our exploitation path at the Blob Registry, because, as I said, it's just a fantastic interface. One of the methods that we can call, so again, Blob Registry hosted in the browser. This is a privileged interface. An unprivileged process is talking to it. So that's the opposite of what we want, right? We want a privileged process talking to our unprivileged process. But one of the things the Blob Registry lets us do is give this array of data elements. And one of those data element types is this bytes provider interface. And this is because we might pass like really big blobs. We might have really big blobs, and we don't want to send all that data just over an IPC message. So if we provide this bytes provider interface, which looks like this, the browser process will call back into the renderer to say, and like, now I'm ready for that blob data. Can you send me the data? And we can see here we have like the prerequisite for this type confusion, right? We have an interface which has two different methods with different return types. So what happens if we type confuse these two return types? Well, at the first level, like the structures I showed you originally, these two are the same, right? You can see there's a structure header and there's a pointer. So bypassing that validation, they validate the same. But if we look at the second level structures there, like the object that that pointer points to, we actually have different types. So here we have an array header overlapping effectively with a structure header. And the interesting thing about this overlap is that when we validate that structure header, so on the right-hand side, the time data, what the validation will do is say, okay, do I know what version this is? In this case, we only know about version 0. So if the version is 0, I want to make sure that num bytes is equal to the size of the structure, so 8 bytes, the size of the internal value plus the head. If the version is larger than 0, we're going to make sure that num bytes is at least as big as what we were expecting. But because we need this forward compatibility, we can't just ensure that it's 0. So when we overlap that with the array header on the left, that means that as long as we set num elements to be bigger than like 0, we can have num bytes be whatever we want as long as it's bigger than 8. And at this point, I would have shown the demo. So you can sort of imagine that there is a Chrome window opening in front here, and then a load of hex characters are written into the HTML. But yeah, so we can use this to read data after the end of an allocation of a size that we control. Or specifically, the allocation has to be at least 64 plus 8 bytes, but we can have it like anywhere between there and a couple of pages. So we have a nice targeted information leak primitive. And this is the point where things get a little bit more hairy. So this is one of the rare opportunities I get to quote myself. This is a slide that I think that Maddie presented a few weeks ago, where she'd asked me for a quote about this bug, and I was like, this bug is just it's the best bug ever. You have so many options to exploit it. It's so powerful. It's just, I just don't even know where to start. Yeah, you should just never say something like that about a bug if you haven't finished the exploit for it yet. Because, yeah, at the start of the week, I still hadn't actually found anything useful to do with this bug. Well, I knew of one useful thing to do with it, and I really didn't want to do it. And I was like, it's such a cool bug. I know that, there's a reasonable chance that whoever wrote this exploit originally, which I haven't seen, will watch this talk and be laughing at how really terrible the way I exploited it is, because there must be a really great way of exploiting it. Yeah. So you go through all of the interfaces where the browser process will actually call into the renderer process. And you're like, okay, some static analysis tooling, I'm grepping the tree for just anything in a Mojo file. There's 10 interfaces that the browser process will call into that have 2 methods with different return types, which is obviously the basic precondition we need here. About half of those, you bypass this validation and you're like, okay, now I can read an integer from out of bounds, once, directly after the end of this allocation. And then I could have given any value as that integer anyway. So this is not helping me, right? About half of the rest are platform specific. I'm I don't want to write an Android WebView exploit, right? I want a Chrome exploit. I want something that works everywhere. So you've got two interfaces left now. And I knew about one memory corruption primitive that I knew this type confusion would give, and I really didn't want to go there. This was a technique that I think Sergey used in a bug report in 2021, which involves Mojo handles. And it got to the point Monday morning I was like, okay, I've got to do the memory corruption thing. There's just nothing else for it. So here goes. We didn't talk about what a handle looks like in the message data before, but we saw, right, we have a block of data, we have an array of handles. When we send a message, when we send a handle, we just put an index into that array of handles. So if we bypass the validation, obviously we can just put that handle index wherever we want after the thing. But there aren't actually any messages that we can type confuse that contain handles. So that's kind of awkward. But fortunately, there is one message that we can type confuse, which contains a native structure. A native structure is really weird, but because Mojo replaced Chrome's legacy IPC and they had lots of code that already existed for serializing and deserializing structures, part of the way they built that was like, okay, normally we'll generate serialization code, but sometimes the developer wants to do it themselves, so we'll give them a way to just like have a buffer and just serialize the data, serialize the C++ object, deserialize the C++ object themselves. But obviously they might need to pass a file descriptor, so we'll have some handles in there as well. And there is one function which can be called in the renderer, which returns a native structure. And obviously that never actually contains any handles, but that's not a problem for us because we can just put some handles in there. Why is this a memory corruption primitive? Well, you're not allowed, for some of those handle types, you're really not allowed to have two of them, right? Like a message pipe handle is a unique handle to that message pipe. So when you copy it out of the message, you can't copy that type. You've got to move it. So the code that handles this obviously moves it. And when we move a handle, we have to put an empty handle in its place. So this becomes a write of 0 where that handle was. So, okay, fine, right? So we have an aligned 64-bit 0 that we can write somewhere after an allocation whose size we kind of control and the offset we control. Which, yeah, starting from this nice logic bug, right, is a pretty tragic way to end an exploit, but I can assure you it's going to get worse. So at this point, I was like, okay, it's like lunchtime on Monday. I need to turn this 0 write into like at least a semi-reliable exploit, because otherwise I can't go on stage. I'll just feel so stupid. And I was like, okay, I like the Blob Registry, but it would be really nice if I could disable validation for other interfaces, because then like I still have a logic bug, kind of, right? Like, so we saw this before. We can actually just, like that's a pointer, right? So if we set this validator field to be 0, then we can just disable message validation on some other interface. It totally works. But as I said, it's like now it's like Monday evening, right? And I have like the groom for this is not nice because the size is really awkward, and you end up, yeah, it gets kind of messy. And you also have other difficulties because suppose that you made like a handful of these as some sort of like small spray. If you send a message that can't validate to one of the interfaces which didn't have validation disabled, your renderer is going to get killed, and then you'll have to start again in another process. So then you need like multiple domains and a load of faffing, and like I did not have time for that. So we need something just like straight memory corruption. Let's go like classic. Back to the Blob Registry, because as I said, Blob Registry is just the best. Blob Registry lets us create allocations. It lets us write data into those allocations. It lets us read the data back. We already use it for a leak. Maybe we can use it for something else. So this is the structure which actually stores that blob data. And depending on how you think about these things, right, we can look at a few different things that we can do by writing a 0 into this structure at some point. The obvious one would be we can change the type of any blob data item to a bytes type. Because for a bytes type, that vector would be populated, and the offset and length would be expected to be reasonable for that vector. But you can't really make files big enough that you'd be able to have an offset that starts looking like a pointer. So this is like you might, on 32-bit, you totally make this work, but on 64-bit, it's not really viable. On the other hand, you could take a bytes object and you could corrupt the vector so that the size checks didn't work anymore, and then you'd get out of bounds right. But that actually doesn't work because the only way you can write into that vector has another copy of the length, which it uses internally anyway. So yeah, it's kind of no-go. And now it's like Tuesday evening, and I'm like, oh, this is ridiculous. But anyone, like the really obvious answer is like staring us right at the top of the screen here, right? This is a ref-counted object. So it has a number in it, which is the number of reference counts. And if you set the number of reference counts to 0, it's probably not the way that's supposed to work. Right, so you can just set the ref count to 0, and then you have like not an ideal situation because you can't drop the reference count below 0. That would be bad. But as long as you can add a reference and drop a reference, you have a use after free. And that's what I did. I'm not really proud of it. It's probably the worst exploit that maybe not the worst exploit I've ever written, but it's not very reliable, and I was kind of looking forward to doing a demo with a 25% chance of a crash, but yeah, that didn't work. So we will not have demo part 2. But yeah, if you're interested to take a look at the exploit or have a chat to me about better ways that you might have exploited this, anybody? Or anything like that, I'll be around this evening. And hopefully I'm almost on time.